corrosion?
Type of corrosion. So we see new types of corrosion that we've never seen before, you're not looking for them. That's what happened on the seawall, okay? It was a new type of, it was very fine cracks in the weld metal. And you talked about the ultrasonics couldn't pick up the crack. Well, that's because the weld metal has these big columnar grains. And the ultrasonics tends to look at those and say, oh, there's a lot more noise in the weld metal with the ultrasonics reflecting off the big grains that you don't have in the base material. So the base material has a better signal to noise ratio on your ultrasonics than the weld metal does. It's not that, well, it's reflecting off the crack. It's not that it doesn't reflect off the crack in the weld metal, but it's also the sound is reflecting off lots of other things adjacent to that, like the grain, the microstructure of the weld. So, anyway.
Just a question, would they have had to replace like the whole top of the pressure vessel, or would they put like a big chunk of steel in there and just build up?
I'm pretty sure they replaced it.
They replaced it. You're gonna have to go in there and do some machining and gouging out. And eventually, they replace a lot of stuff off the top. You don't just put a patch in. I remember what I was gonna say about 30 Mile Island. On the first 2 days, or first day and a half, they called it stress corrosion cracking. And it was stress corrosion cracking. But then some attorney for GPUN read their insurance contract where it excluded corrosion. Okay? So after a day and a half, they had called it SAC, stress assisted cracking. Well, what type of cracking is not stress assisted? Okay? You don't get a crack unless you have stress. But they needed to get that corrosion word out of their press releases. And that was one of their problems. Because initially they said, stress corrosion cracking. Oh, the exclusion in your insurance policy says we don't cover corrosion. Then we got into the debate of corrosion is a slow, gradual process. If something occurs in 30 minutes, is it a slow process? Well, you say no. Okay. With this thing went to, what is this one? It's another one. We went to arbitration. This had to do with, it was in Ohio. It was a graphite pressure vessel at a refinery of some sort, a chemical plant of some sort. And the question was, did it explode or did it collapse? Because explosions were excluded from the policy, okay? Collapses were not, okay? So I remember going to the arbitration. It turns out at the arbitration, the chief arbiter was the former vice president of American Nuclear Insurers, which were the ones who insured the 3 Mile Island thing. And so this guy knew me from that, okay? I was working for him then. But anyway, we go into this arbitration. This has nothing to do with anything other than, so this attorney, big shot attorneys asked me questions here in downtown Boston about what's the definition of corrosion, what's the definition of an explosion. By the way, the word explosion comes from the Latin, which means to clap or make a loud noise. So it turns out explosions make loud noises, okay? Collapses can make a loud noise too if you have something that's 3 stories tall and it collapses. And again, so anyway, he's asked me these questions about how to define these words, and finally he just gets frustrated with my answers. He says, Dr. Ear, are we just going around in circles? I said, you may be, sir, I'm just here for the ride. Everybody cracked up except that attorney. Anyway, it's good to learn to get smart about the answers. Yeah. Let's see. I must have jumped ahead. Okay. Today we're going to start aluminum. How about? Oh, no, we're not. Sorry. We're going to do nickel-based alloys. Okay. We're not going to spend very long on nickel-based alloys because there's not that many of them used, although the Navy uses a lot of them. Copper, nickel, Monel. There's actually, this basically is straight out of Lippol's other book, which is, I'll keep it here anyway. John Lippol wrote a book on, he's a welding metallurgist, on welding, metallurgy, and weldability. which is the most recent book. The first book he wrote was Weldability of Stainless Steels, which he wrote with Damien Kopecki. And then he wrote a book on weldability of nickel-based alloys with John DuPont at Lehigh. So this stuff is all out of his book, and it should be on Stellar. We still don't know what's happening with Stellar. If you try to go to your course numbers, like 2821 or 371, I can't even get anything off those. But if you go to 3S171, you guys are now authorized. Hopefully you can see all this stuff off that, yeah.
It looks like we were gained into it too, so if you're registered for it, you just click on like you at register, it'll
Yeah.
bring up the S171 something.
Oh, okay, so my secretary's been working on this over the last 3 days. And why the registrar can't figure this thing out, but you gotta remember, people like to think of MIT as a technologically sophisticated school. We got out of manual registration about 10 years ago. All the other universities in the country were doing computerized registration, but MIT was still filling out, carbon paper and things like that, even 10 years ago for registration. We have a registrar who is not using some of the resources available around here. Anyway, so nickel and nickel-based alloys. The problem with nickel alloys is they're expensive. You're talking, I don't remember what my numbers were, but I think it's $6.50 a pound for nickel. Okay, just as pure nickel. And we use commercially pure nickel for some situations, but like most pure metals, it doesn't have very, very high strength. So we can strengthen it by adding copper or molybdenum or iron or chrome and iron. Well, nickel chrome iron is like stainless steel, except instead of 18% nickel, 8% nickel and 72% iron, it's got 72% nickel and 8% iron. Okay, we just switch the iron and nickel ratios, and then these nickel chrome moly tungstens and nickel iron chrome moly alloys and the cobalt alloys. These things have been around for 100 years. There was a guy Elwood Haynes who was from Indiana, and he was interested in he was a metallurgist, and he started making some of these alloys, and they were better than the stainless steels. Okay. They're also a little pricey if you start looking at these elements, but they did have better corrosion resistance. So we tend to use these in all kinds of applications, and the alloys haven't changed a whole lot in the last 80 years or 60 years because they're not used in huge volumes. There's not a huge market out there to improve these things. It turns out until people started learning how to weld zirconium, because we learned how to weld titanium. Titanium and zirconium, if you look at the periodic table, are right above and below each other. That's the periodic table. There's titanium, there's zirconium. Zirconium's the cladding on your reactors because boron's a poison. Zirconium has a lower neutron cross-section, actually maybe the lowest in the periodic table, I don't remember, but it's very low. Hafnium, which is below that, you're going to make this zirconium really pure because a little bit of hafnium will poison that zirconium, okay, in terms of the hafnium is a poison for neutrons, just like boron. But anyway, we did a lot more welding on titanium from the 1950s and stuff. It wasn't really until the 1980s or 1990s we really, from the titanium, we learned how to process the zirconium. And so people always use a nickel molybdenum alloy, okay, for the reactor vessels for making acetic acid. And acetic acid is the highest volume chemical of organic acids. We make acetate films, we make all kinds of plastics, we make pharmaceuticals. It's just a raw material like wood or steel, okay? The largest inorganic acid is sulfuric acid. Almost all the gasoline goes through a sulfuric acid catalyst and things. So anyway, about the only thing that is corrosion resistant to the acetic acid in the manufacture of acetic acid was this nickel moly alloy. There's nothing special about the alloys. The Monels were really just nickel copper alloys, and yeah, they changed them a little bit, but they're about the same as they were 60 years ago. okay? There's not a lot of sophistication to this, okay? And like there is in the aluminum or the, certainly not steel, like steel. But then you get over here to the precipitation strengthened, and these alloys have titanium or aluminum, which formed intermetallics, very high melting intermetallics. Nickel 3 titanium melts at like 2,000 degrees centigrade. Nickel melts at like 15 or 1,600 centigrade. The alloy can have tremendous high temperature strength. These are the workhorse alloys for jet engines, okay? Nickel-based superalloys, okay? So lots of sophisticated work on the precipitation strengthened, not very weldable alloys, but hey, in general, we don't weld turbine blades, okay? If we could, we would, but they're not very weldable. You can do some repairs on them, but these things, on the other hand, hey, they're just simple old, 80-year-old metallurgy, and we do weld on them all the time. There are some specialty things that we don't have to worry about. The intermetallics, it's sort of a research project for Oak Ridge National Lab. Okay, they get tens of millions of dollars every year poured in a trash can. Okay, to try to develop these alloys. And then oxide dispersion strengthened alloys, where you have very fine oxide inclusions to strengthen things. So if you go through Leopold's book, he'll tell you which alloys go with what. This gamma prime, it's the nickel, aluminum, titanium phase, intermetallic phase, and if you get that as a precipitate, you can get very good high temperature strength. This alloy doesn't dissolve until about 1,200 degrees centigrade in an alloy that melts at around 1,350 centigrade, okay? So it maintains its precipitate to very high temperatures. Nickel 3 niobium is gamma prime. It's a similar type of high melting, but we call it the gamma prime. The niobium and the titanium we're going to see are much more weldable. Nickel 3 aluminum, just stay away from it. It's very difficult to weld without getting cracked, okay? And then they throw in all these other things as carbide formers, and these, you have to worry about, well, you can get high temperature strength in these superalloys for jet turbines by creating some of these different phases, sigma, P phase, mu phase, Laves phase, called topologically close packed phases. And these are some of the alloying elements that promote that. Some of these can be very brittle in stainless steel. The sigma phase can brittle the steel. And then we put chromium and aluminum. Those are the two things that give you good high temperature strength. So if we go back to our alloys, the nickel alloys are used for corrosion resistance, primarily solid solution, and high temperature strength in very high temperature. I mean, these are our workhorse materials for very high temperature processes where we're getting above the stainless steel, which is, let's say, 600 degrees C is about as high as you want to go with stainless steel. And you can get up to 1,000 C with some of these things, maybe even 1,100 in some cases. Okay, one of the problems with the type of alloys the Navy uses, like the Monels, they are the model system in the laboratory for developing solidification cracking. Okay, if you want to study solidification cracking, you won't find a better system than nickel copper alloys. Okay, and it has to do with the grain structure of welding. If you make a very deep weld and you don't have or you have something that has sort of an elliptical shape, your last part to solidify will be this stuff in here. You get rejection of the solute. You have to make sure the fillet welds have the right shape. If you have a concave shape, the last stuff to solidify will be like this. It'll form a nice little crack, okay? If you look at the microstructure of these things, this is what happens, okay? Basically, the stuff as it shrinks, it's sort of this slurpy type material, okay? It's got a liquid boundary with all these solid dendrites. You can think of the solid dendrites as the ice crystals, and the liquid is the syrup, okay? In there, and as it shrinks on solidification, you end up with these nice little cracks all through here, okay? So, now sometimes some of that liquid, particularly sometimes you have to squeeze on it or something, you actually can squeeze some of that liquid into the cracks, and they call this self-healing. Bull. It's still a weak spot in your material, okay? Maybe it's not a real crack, but it's still a weakness. Now, it turns out the only spec I've ever seen, and I had to try to qualify this for a company, back I told you, I've done, for 5 years I did hundreds of failure analyses for this engineering firm down south of here. And it turns out there is a company in eastern Massachusetts that was making some electron beam welds for Navy reactors, okay? And it was in these nickel-based alloys. And they're so prone to cracking that Bettis, Westinghouse Bettis, which is one of the Navy still has, I think, two labs for the materials and design. I mean, General Electric Knowles Atomic Power Lab and Westinghouse Bettis. They've been downsized a lot since you designed the reactors in the 50s and 60s, but they still exist. It's one of the few areas in the government where you still have competing labs, okay? Which is an expensive way to go, but again, it comes out of NR's conservative, okay? So they have competing labs. But in any case, they had this, you could make this electron beam weld. It was about a half-inch thick material. I don't know what part of the reactor it was. All I got was test samples, because these guys are doing electron beam welding here in eastern Massachusetts. There's a lot of electron beam welding shops in New England compared to other parts of the country, because some of the first electron beam welding was done down by Pratt & Whitney in Connecticut and General Electric Lynn. It was for the aerospace industry. And a bunch of European companies came over, there was experts in electron beam, kind of came over into Connecticut or Massachusetts or whatever, and they're still here. So if you need to get electron beam welding, a little shop, mom and pop shop will do it. They're still around here. In fact, one of the earliest ones was started by in terms of welding professors at MIT, it was, if you go back historically, it's me, Professor Matsubushi, you go back further, it's Mel Adams. Mel Adams in the 60s started an electron beam welding shop. It was just up here in Woburn. Okay, it was his consulting business. Anyway, so they'd make these welds, and they had to magnetically spin the beam to get a sharper, a wider weld. But then they had to overlap it by 30%. They had to make another weld right next to it. And they had to do this without any cracks more than about 1 millimeter in size. Well, wait a second. This is the first spec, the only spec I've ever seen in welding where cracks are allowed. Okay? But they had to be smaller than about 1 millimeter, because obviously they needed this alloy for corrosion resistance. They found they couldn't weld it without cracks, and so they went back and they did the fracture mechanics and says, okay, if the cracks are no bigger than, we can live the life of this thing, okay? Well, those guys tried to qualify those welds. I was getting samples. For 6 months, they kept on sending in samples. They were spending a fortune. They couldn't get their beams operating precisely enough. I kept on failing. They didn't have a choice. I mean, they were failing the spec. I don't know what they finally did. But
not a new consulting site.
Yeah.
I wasn't a consultant. I was just a metallographer here, guys. I mean, they wouldn't, because it was NR, you know, I was going to have a security clearance for them to tell me what they were doing or how they were doing it. But anyway, you do get these kind of, well, a solidification crack in a nickel-based alloy, okay? They occur all the time. And so Lippold came out of, he did his thesis at RPI, and the big name there was Warren Savage. And in welding, he was the top guy in the 1970s in welding in the country. And he developed lots of cracking tests, and this is one called the Transverse strength test. You take a gas tungsten arc torch, and you lay a weld bead on your material, and then while you're welding, you just deform it in place. So now you're putting a big strain on it while it's solidifying, and then you go along and you look for cracks, and you find them, okay? And you find how they form, you find the microstructure.
This is a testing process.
This is a testing process, okay? So, we know how to design the alloys. They were designing these alloys in the 50s and 60s. And Savage was doing his research in the 60s and 70s for the high alloys companies that were making these alloys, trying to improve them. You get cracks, it's a sort of, if you make a big enough weld, you're gonna have some cracks. And the question was, how did you get enough cracks so that you could find out which were the most resistant things? And so I think I told you that when I started in this business, most of the welders thought the only way you solve a welding problem is welding metallurgy. And I told you that Maslow's statement that the only tool you have is a hammer, every problem is a nail. And so I remember sitting in my first office here at 8137, the first year I was here, and saying, boy, I don't want to compete with those half dozen or dozen Warren Savage students who have all been brought up on welding metallurgy. If I'm going to do welding, I'm going to have to do something else. So I chose welding processes, the physics and chemistry of the process. And so you still see, and Lippol's 3 books are a good example of everything's welding metallurgy. NR, or not NR, but NAVC tells you guys to take a welding metallurgy course. They don't tell you to take a welding course, they tell you to take a welding metallurgy course. Well guys, it's not the only way to solve the problem. And in fact, we did learn to solve a lot of these problems. I told you that they're sort of not problems anymore after 50 years. We know how to control the metallurgy and the composition of these things so that we don't have these problems we had when we were developing the alloys. The problems today are more process problems, like can you keep the moisture out of your shielding gas, or can you keep the lube off the wires, or things like that. And we're having the same problems that we had in the 1930s with hydrogen cracking. It still shows up, okay, in various forms, okay. So the other thing about the nickel-based alloy, this actually is out of one of Lippol's books, but he stole it from somebody else, Decker and Sims, who wrote a book on nickel-based superalloys before him. And this is not a weld. In fact, this is an artist's conception of a microstructure, okay? This would be increasing aluminum or titanium. And here you have nearly pure nickel, and over here you have a nickel-based superalloy that's like it's going to go in a jet engine, turbine blade. And you start out with something that doesn't have anything except a few M23C6 carbides along the grain boundaries. These are similar to the carbides that cause the chromium carbide sensitization in stainless steels I told you about. You get grain boundary cracking, cracking of the grain boundaries because you form these carbides. You get it in nickel-based superalloys too. It doesn't have to be an iron-based alloy, it can be a nickel-based alloy. That's over here. As you move over and put more and more chrome and aluminum and titanium, you'll start getting MC carbides. So this is one metal atom for every carbon atom. And these MC carbides form at higher temperatures. They're sort of blocky. You do start to get some of these gamma prime. This is as you're adding titanium or aluminum. You get some of this gamma prime nickel-3 titanium. And you get a few of these precipitates. You keep on increasing the concentration. Your grain boundaries start getting more carbides, and you get more and more of these gamma prime precipitates. You get over here to even higher concentrations, and all of a sudden these gamma prime precipitates start to become kind of square rather than round. And there's good crystallographic reasons for that. And you get to volume fractions of the nickel through the gamma prime phase that can be 85% intermetallic, surrounded by some solid solution. And that's what gives you the really good strength, okay, at high temperatures. But you can also get nodules and stuff, and you have to process it, and you have to forge them if they're not cast, but some of the turbine discs and things. You have to forge them the right way to break up some of these original solidification structures. Or if you don't start with a great big casting, you can do what the Air Force has started to do. You spray these alloys into fine powder, solidify them that way, so you didn't get these big coarse blocky carbides and intermetallics and stuff. And you don't have to break them down by forging, but you basically take those powders and now you consolidate the powders, which are already fine grained, okay? You get a more uniform structure without some of these big blocky ugly things. You still want the blocky gamma prime precipitates, okay, but you don't want these regions which are segregation of different alloying elements during solidification. So there's a whole problem of, you don't really like casting to start your alloy because it gives you big blocky, kind of like raisins in a plum pudding or raisin bread. You don't want those raisins, you want little currants, okay? Okay, small things, finer grain. And if you make it by powder metallurgy, you can hopefully get more uniform, more homogeneous, and get even higher temperature properties, yes.
Yeah, so we could just, I was thinking about this and thinking about how you have these little stretches, and you explained how on a submarine, we kind of, not heat treat, but pressure treat this by deep dives, right?
Right.
So I just was hoping you could reconcile that, like, what seem to be two conflicting ideas, because like, the hull of a submarine is rated for a certain period of time, right?
Right.
And so the implication is that, like fatigue stresses or something over time are gonna wear this out, but at the same time, going deep kind of makes your material stronger and alleviates a lot of stress from it.
By relieving one of those circles, the stress circle.
Okay.
Okay, going deep gets rid of, remember I got my 3 interacting circles? The metallurgy circle or the microstructure circle is 1, and there's only so much I can do after I've made my material.
Okay.
Then there's the stress circle. If
Okay.
I relieve the residual stresses, I shrink that one. If I keep it nice and clean, my environment, and don't let hydrogen get in there, I relieve that. Or if I don't let boric acid get in there, okay? If I keep the system clean by my process or by putting hydrazine in on shutdown, okay, to keep the oxygen out of the water, I shrink that circle. The microstructure, the metallurgy, actually this is a good point of, you can't solve all the problems in the metallurgy circle, okay? Some of them you have to solve in the mechanical behavior circle, which is residual stresses. Some of them you have to solve in the corrosion circle, which is the environment, right? If you want to think of it that way. When General Electric had their big stress corrosion cracking problem, they worked on all 3 circles, okay? One of my problems with most of the philosophy of welding in this country right now is everything's in the metallurgy circle. Well, you don't solve it just looking in one area, right? You attack a problem, you attack every area, okay? So, anyway, did that answer your question? I don't know if it did.
Not exactly. I guess my real question was, you submerge and strengthen your hull, but also over time, your hull's gonna fail, like another thing, right? So what is it? Is it like pre-existing flaw resulting in like brittle fracture of a hull that you're afraid of? And what exactly
Now, the quality of the submarine steel, you're not, a surface ship, it's corrosion and thinning, okay, it gets too thin. Submarine steel, that hull would last a lot longer. It's all those other components
I
inside.
guess I'm curious, like we had this in Los Angeles, that they wanted to extend the lifespan like a year and a half or something like that before we decommission. So they have a review, and they look at the hull and I guess do an analysis of that. So it's just something that occurred to me while you were talking about this, and obviously there's some kind of analysis, but it seems like the hull, especially after you pressure harden it really, after your first depth dive, it's gonna last you, as long as you're preventing corrosion, which the Navy is meticulous about that, it's gonna last forever, so that's really not a limiting component.
Well, that's assuming you never cut through that hull in the previous 30 years.
Okay.
But I remember seeing a picture of the Patrick Henry back in 1988, and it looked like a patchwork quilt
Right.
of all the penetrations.
Yeah.
If you just built your hot dog and never touched it for the next 30 years, it will last for that hull will last for another 30 years or 100 years, as long as you keep your zincs on it or your cathodic protection. But when you start going and starting welding other things on it, it no longer has that 30-foot diameter circle or 20-foot diameter circle accurate to how many millimeters on the diameter? Okay, not very many, right? That's a pretty perfect circle. Once I've gotten to be 30 years old, I've done so many, that thing doesn't have the same depth capability because it's no longer, it's an externally stiffened cylinder.
Okay.
And it's now no longer a cylinder. It's sort of a bumpy cylinder, right? And so it may be things like that. I bet they had, when they did it, they were measuring diameters at different positions, and they were kind of saying, well, is this hull worth saving? But it's not from corrosion or metallurgy of the hull. It's from the structure. the geometry of the hull.
Okay.
If it failed in the hull, most of the ships, except Coast Guard ships, they corrode away to nothing, pretty much, okay? They're held together by paint at the end, okay?
Yep, well done.
Okay, but the Navy ships, it's not really the hull, it's all the components inside. And you're advancing the technology so rapidly that they want to build a new ship. Who wants the old ship, right?
Okay, fair enough.
So, no one wants, you don't want to be assigned to a 50-year-old ship. That's the Coast Guard. If you want to do that, you can go to the Coast Guard. Okay, we gotta stop, sorry. Sorry to run over. I got it. Thanks, Alan.